Once again, you're welcome here. Today we'll be looking at investigating the specific heat capacity. We'll be looking at investigating the specific heat capacity. This is for the alternative to practical paper. This is for paper 6. Here we're going to describe an experiment that shows how to conduct this or find out about the specific heat capacity in any given material, in any given substance. So the first thing we do when we are doing an experiment, we have to demonstrate or we have to show the aims of the experiment. So in paper 6, when you write this, you have to, when they say describe an experiment on how to investigate the specific heat capacity, so what you need to do is to plan the experiment like this, the way we're going to describe it. So the first to do is to show the aim of the experiment. So the aim of this experiment is to determine the specific heat capacity of a substance. So the aim is simply to describe, to demonstrate, or to determine the specific heat capacity of a substance. We can only do this by linking the decrease of one energy stored or the work done to the increase in temperature and subsequent increase in thermal energy stored in another. So here we're going to also talk about the variable. After we write about the aim of the experiment, the next thing to say is to talk about the variables. So here we mention the dependent variable and the independent variable. So the independent variable is that variable that the experiment do not depend on. When you say independent variable, the variable that the whole thing is not depending on so much. One of it is time. Time is an independent variable in this regard. The dependent variable is that variable that the whole experiment will need, will be depending on. That is temperature. So because you remember, when we talk about specific heat capacity, we talk about the change in temperature, initial temperature and final temperature. So it's a dependent variable in this experiment. But time, if you look at the formula, there's no time in the formula. When we say the energy, remember the formula last time? We said the energy, we say the energy E or delta E, the energy delta E, that should be better, right? Energy equals to M C S small delta T, right? This was our energy formula, delta T. So you can see that this delta T is a change in temperature. So this is a dependent variable. The whole experiment is depending on the temperature, right? The whole experiment is depending on the temperature. It's a dependent variable, and because if you're looking for the Cx, if we make this the subject, we said Cx is the energy or change in energy. Energy or change in energy, remember you can write the change here, is equal to Cs is equal to change in energy divided by the mass. That's making this the subject of formula. Making the Cs the subject, it will be this divided by this and this. Divided by the mass, and the delta T. Divided by the mass and delta T. So you can see this change in temperature is a dependent variable. To find the specific capacity from the formula, you can see that this temperature is a dependent variable. But there's no time here. Time is not part of the formula. So time is not a dependent variable in the experiment. It's not a dependent variable. So to obtain the specific capacity, time is not a dependent variable that you go to solemnly depend on. Time is not a dependent variable. But temperature is a dependent variable. Temperature is a dependent variable. Mass is a dependent variable, right? Mass of substance is a dependent variable. Temperature is a dependent variable because it also changes. Okay, temperature also changes. Now let's take a look at the next one. Okay, So after noting your dependent and your independent variable, the next thing we're going to look at is the control variable. What are those variables that we can control in order to get our result? The control variable. So you mentioned the dependent variables, you mentioned the independent variable, then we talk about the control variable. You mentioned them. You have to mention them. The one you can control, the material of the block, the nature of the material, what type of material you're going to use, is a control variable, right? Then the current supply, you can control how much current you supply to it. You can control how much current you're supplying, right? You can increase the current by reducing the resistance. Okay, you can determine how much current you're going to supply to it, current supply, or the voltage, the potential difference, what we call the voltage. Voltage is called the potential difference. The voltage is called the potential difference. So the voltage you have applied, that's the how much battery, maybe stronger battery or weaker battery, the current, and the type of material. These are the control variables. So when we talk about control variable, let's itemize them here. So when we talk about control variables, are those variables that we can that is within our control, either to get faster or quicker what we want. The control variables are one. Control variables are one. Nature of the material. You can say nature of the material or material type. Nature of the materials. These are within your control, right? Nature of material. Nature of material. These are within our control, right? What type of material we're going to use, okay, is within our control. Number two, amount of current. The current. And then number three is the voltage. Number three is the voltage supply or the potential difference. Remember, voltage is the same as potential difference. Number three is the potential difference, PD, or the voltage, what we call the voltage you are supplying. The voltage you are supplying. Remember this formula that relates voltage is equals to the current multiplied by resistance. Remember this formula that relates voltage is equals to current I multiplied by resistance. Okay, remember this formula. So and also remember that we said the energy formula in electrical circuit. Energy is equals to IVT. So the current you supply is a control variable. The voltage that is applied is a control variable, but the time is an independent variable. Remember the energy formula. So if I call this my equation 1 today, I call this my equation 2 today, and then I call this my equation 3 today, and then this one will be our equation 4 today, right? This will be our equation 4. So let's take a look at these equations as they apply to our case. So we know the independent variable. The whole experiment is not solemnly dependent on this variable, is time. Then we have the dependent variable. Everything is dependent on this is temperature, right? Temperature is a huge dependent variable in this regard, or mass. It's a huge dependent variable. Then we have mass is a constant, right? Mass is a constant, so it's not even a dependent variable. Then we have control variable, the one you can control the nature of the block that you use, the current supply, and the potential difference. Now let's take a look at the equipment listing. Everything that you need for the experiment and their purpose, what they'll be used for. Now let's talk about the 1 kg block of metal. Metal you use is aluminium. 1 kg, you're using 1 kg block of metal of aluminium, or a beaker containing a known mass of water. Or you use a beaker containing a known mass of water. Maybe that mass is maybe 1 kg mass of water, but it's a known mass. Now, what do we use this for, or what's the purpose of this? Why do we need this? The purpose is the substance to calculate the specific capacity. You know, if you want to calculate the specific capacity, you need a known mass, right? You need a mass. It's necessary for calculating the specific heat capacity of the material. Now, thermometer, you need a thermometer to measure the temperature of the substance, right? The reason why we need a thermometer in the experiment, we need a thermometer in the experiment. We're going to show you this. We're going to show you, see. We're going to show you, this is the experiment, the diagrammatical illustration of the experiment. Okay, here, under your method, you draw the diagram. You draw the diagram and then you explain the concept, what is happening here. Okay, but before then, let's quickly look at the equipment that you need. We talk about thermometer to measure your temperature, right? To measure the temperature rise, in case there is a temperature rise. Okay, you already take note of the initial temperature. You've taken note of the initial temperature. Let's say the initial temperature is, let's say 50. Then when you supply heat, and the heat comes from the electrical system. The heat comes from the electrical system. You heat them up with the electrical appliances, and then you supply, this is the energy supply system, and you heat this metal, and then temperature, at a point maybe temperature will be like 90 or 100, so you can see the temperature rise. At the beginning you know the temperature, initial temperature, and then later you measure the temperature rise. Okay, now that's what a thermometer is used for. Immersion heater to heat the substance. We bring the immersion heater to heat the substance, right? We bring immersion heater to heat the substance. Okay. Now, then the next one is the power supply. To supply power to the heater, you bring a power supply. You bring a power supply. This is a power supply. This is a power supply. You bring a power supply to supply power to the heater. Because if you don't bring power to the heater will not be able. This is the heater. Look at the heater. Look at the heater from this place. From this place to this place. This is the heater. Okay, this is the heater. You bring power, you supply power to the heater. This is a voltmeter that is measuring the amount of voltage. This is an ammeter measuring the current. So this ammeter is measuring the current that is supplied by this this power supply. This power supply is supplying the power to this place. Remember, power is equal to IV. Power, I think we also need to write that formula. The power is equal to IV. So another question. Power, we know energy is IVT. Power is just IV. Power supply is equal to IV. Electrical power supply here is IV. So we got this equation 5. Okay? We got this equation 5. Now still on our discussion. Then we say the power supply is to supply power to the heater. The heater, immersion heater, is to heat the substance. Is to heat this substance. This heater is to heat whatever substance, this substance. In this case, we are heating an aluminum block. Okay? Whatever you are heating, if you are heating an aluminum block, you are heating whatever metal you're heating or water, the job of the heater is to heat whatever substance that you put here. The job of this power supply is to supply the energy that is needed to heat, that is needed by the heater to heat the substance. Then whatever the ammeter is just to measure the current, amount of current, and the voltmeter, don't let this one confuse you. They are just ammeter and voltmeter. Ammeter is to measure the amount of current that is supplied here, and voltmeter is to measure the amount of voltage or potential difference that is applied to this system. Okay? Then we also have what we call the stopwatch. We need the stopwatch. Okay? You have to just hold a stopwatch. What do you use it for? To measure the time taken for the substance to heat up by a certain temperature. The time it takes. Okay, you just measure it. Remember, it's just independent variable. It's independent, but you just need to measure it. You just need to measure it anyway. Despite the whole experiment is not depending on the time, because the time is not like the factor in this regard. However, you need to measure the time it takes for the substance to be heated. So you have to measure the time taken for the substance to heat up by a certain temperature. So let's say the former temperature was 24, now the temperature has changed to 25. So how long it took for the temperature to increase from 24 to 25? So you just take measure of the time using a stopwatch. Then you need a voltmeter to determine the potential difference through the heater, to measure the potential difference or the voltage through the heater. And then you need an ammeter to determine the current from the power supply to the heater, to measure the current from the power supply to the heater. Now here are your resolution. Here are your resolution. And resolution means the smallest division on the measuring instrument. Okay? It can also be described as the ability to see two structures as two separate structures rather than as one fuzzy entity. Okay? Now, the resolution of the measuring equipment is thermometer is 1 degree Celsius, right? That we just want an increase in 1 degree Celsius. Remember when we defined specific heat capacity yesterday? We said specific heat capacity is the energy required or the energy needed to raise the temperature of a substance through of 1 kg of a substance through 1 degree Celsius. Okay? The amount of energy that is required to raise the temperature of a substance of 1 kg of a substance. Always remember 1 kg. To raise the temperature of 1 kg, 1 kilogram of a substance through 1 degree Celsius. So because of that definition, we know that we've resolved that the thermometer has to increase through 1 degree Celsius, and the stopwatch was 0.01 second. That this were your result, like some of your results you found. And then the voltmeter was 0.1 volt, and your ammeter was 0.01 ampere. So these are some of your resolutions, some of the results you got, okay, from this. Now, this is the description of how this is set up, okay. You start by assembling the apparatus and placing the heater into the top of the block. So we've shown the diagram. You place the heater on top of this block. That's where you start from. You start the connection by placing the heater on top of the block. Then you measure the initial temperature of the aluminum block from your thermometer. You take thermometer before you supply heat. Before you supply heat to the heater, use this thermometer to measure what? The initial temperature of this block. Measure the initial temperature of this block. Then connect the heater to a power supply. Connect the heater to a power supply. Turn on the power supply and start the stopwatch. The next thing is to turn this on, the power supply. After connecting them, you turn it on and start the stopwatch so that you can measure the time it takes for this to happen. Then, while the power supply is on, the heater will heat up the block. Once the power supply is on, the power supply is supplying already electrical energy to the heater. Then the heater will start to heat up the block. Okay, it takes several periodic measurements, e.g., in every 1 minute of the voltage and current from the voltmeter and the ammeter. So you see the different value. In every 1 minute, the values will be changing. The values of voltage and current from ammeter and voltmeter will be changing respectively, right? Then calculate the average. After that, you calculate the average. After 10 minutes, you calculate average, okay? So then after that, you switch off the power supply, stop the power supply stopwatch, and leave the apparatus for about 10 minutes. And the temperature will still rise before it cools, okay? After that, you switch it off and leave the apparatus for about 10 minutes because before the temperature starts to cool, it will still rise. That's why you stop supplying heat. Then eventually it start cooling. Then you monitor the thermometer and record the final temperature that it has reached for the block. You measure the thermometer and see what final value it reached before it starts going down. What final value, and then you will take that final value and you're going to use it for your calculation. So this is your table. Now after you've described it, okay, for your paper 6, after you've described, you read the description or your method, you put diagram and this small explanation together for your method. Then you draw a table. You put your time, 60 seconds, which is 1 minute, 120 seconds, which is 2 minutes, 180 seconds, which is 3 minutes, 240 seconds, which is 4 minutes, 300 seconds, which is 5 minutes, 360 seconds, which is 6 minutes, 420 seconds, which is 7 minutes, 480 seconds, which is 8 minutes, 490 seconds, which is 9 minutes, 600 seconds, which is 10 minutes. So it's like you do from 1 minute to 10 minutes. But we're putting them in seconds because time, the standard unit of time is in seconds. So instead of writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for time, instead of taking measurement as the time progresses, in 1 minute time, you record your potential difference from your voltmeter, from this device, from this one. You record from this device. The voltmeter, you measure your potential difference. You see this value will be showing you. It will be displaying here. Okay, the voltage will be displayed here, or what you call the PD, potential difference. So in 1 minute, you see this deflection. This arrow will be deflected, maybe to 0.1 or 0.01 or 1 or 2, whatever value it is, it will be showing. But they are calibrated there. The numbers are given in real life. Okay, then after you measure the temperature, you also measure after you've measured the voltage from the voltmeter, or the PD, potential difference from the voltmeter, you also measure the current from the ammeter. You also measure the current, because simultaneously, as this value is displayed, this one is also displayed. So you measure the value. In 1 minute, also measure the value from the ammeter to get your current. You remember the ammeter is for measuring the current. Is that okay? Your ammeter is for measuring the current. So you do the same. When the time has progressed to 2 minutes, which is 120 seconds, you also measure the potential difference here, and you measure the current from the ammeter here. Then in 3 minutes, you measure the potential difference from the voltmeter here and record it here. You measure the value of the current from the ammeter and record here. Like that, you get to 10 minutes for either of them. So after that, you find the average. How do you find the average? You add all the values you get here, all the values you get, you add them together, divide by 10, because they are in 10 places. You add them up, sum them up, and divide by 10, you get the average value. Same for the current. You add them up and divide by 10, you get the average value, right? Then you write your initial temperature also. See, this is a dependent variable. Temperature is a dependent variable. C is on its own. See, it's a dependent variable. These are control variables, the potential difference and current. They are control variables. You are controlling them, right? You are controlling them. Then the dependent variable is the temperature. So you write your initial temperature before you switch the heater on. Before you switch the power supply on. Before you switch the power supply heat to the heater. Before you switch it on, you write your initial temperature. And then when you switch the power supply on and the temperature has got it to the highest level, you also take the maximum temperature or the final temperature and write it down. Then the next one is your analysis of result. So we've done this analysis of result. The thermal energy supplied, we've given this formula. Remember, in our equation, we've given this formula. The energy is what? Energy is IVT. That means current times voltage times time. Current times voltage times time. Current, I is for current. This is the symbol of current. Current times multiplied by voltage multiplied by time. Okay? That's for that. So you calculate your energy by using your average current. Your average current, you calculated your average current here. So the value you got for your average current multiplied by the value you got from your average voltage and multiplied by the time. Okay, 10 minutes it took 10 minutes for all, right? Or you add all of them, divide by 10. You get the average time. Or you just take 10 minutes for that. So you use to multiply by the time it took you to get those values. Okay? Or you find the average time as well. Add all of them, divide by 10. And then you multiply. You get the energy, right? You get the energy. So remember, E is the thermal energy. You see here now they are using E for energy. E is the thermal energy in joules. I is the current in amperes. The unit of current is ampere. The unit of current is ampere. The unit of potential difference is volt. The unit of time is seconds, right? Now, the change in thermal energy is defined by this equation. The change in thermal energy. You remember we did this in the previous class. The change in this energy is, remember we're looking for specific capacity. So the mass times specific capacity is change in temperature. Okay? So once you get your energy, you take the value, whatever. The first step is to calculate the energy. Whatever we get for the energy, we bring it here, we put it here. Let's say we get 450,000 joules for energy. After calculating, getting the value of our energy that is supplied to the aluminum block, You bring it here. You say that energy is equal to the mass. You already know the mass of the aluminum block times the change in temperature. You know the change in temperature. So you are going to make the specific capacity the subject. So like this one, like using this formula from our board. Using this formula. Equation 2. Now, you calculate the specific capacity from this formula. You say the energy you just calculated, using your current, your voltage, and time, you got your energy. That's this one, this energy formula. This energy formula. After you calculate this energy, whatever value you get, then you come and put it here to find your specific capacity. You come and put it here. You say the energy divided by the mass. You know the mass of the substance you're using. Divide by mass times the change in temperature. Once you divide the energy by the product of mass and temperature, you get your specific capacity for that substance. You get your specific capacity. So this is how to determine the specific capacity of a substance. This is how to determine the specific capacity of a substance. Are you with me? So this is the formula, but you have to make this C or CS the subject. So when you make it the subject, the energy you've calculated from IVT, electrical energy, that's the current times voltage times time, that energy you obtain from that IVT, current times voltage times time, that energy, you will divide it by the product of mass and change the temperature. You divide the energy by the product of mass of the block, of the aluminum block in this regard. In any other regard, if you use another material, you divide by the mass of that material. So you divide by the mass times the change in temperature of the difference in the initial temperature and the final temperature. So, or you can find your change in energy by saying to calculate change in energy is a final energy, which is IVTF, that's minus IVTI in the final time minus initial time. So you can calculate, you can actually calculate change in energy like this. You know, the I is the current, V is the voltage, T is time, final time. Final time was 600 seconds. The final time was 600 seconds. Then the initial time was what? 60. So you can just say the change in energy is the current I, which is whatever the average value you get from here. Whatever is the average value you get from the current. Average to add all of them, divide by 10. Whatever value you get from the current, average value of the current, multiply by the average value of the voltage, whatever you get as the average value. Average value is all the value you got here, add them together, divide by 10. You get the average value. So the average value of current multiplied by the average value of the voltage, then multiply by the final temperature, then minus the average value again of current times the average value of voltage, multiplied by the initial temperature, like in this regard. Okay? So you can also calculate change in energy like this. Change in energy, so equation 6. Change in energy is equal to the IVT final, that is the final time, minus IVT initial. IVT, that's initial time. Okay, this is our equation 6. So you can use this formula to calculate your change in energy. Is that okay? If you so wish. Okay, but anyway, we've gone past this. We've even calculated the energy and we've calculated the specific capacity. The CS is equal to the change in energy, whatever change in energy you calculated, this change in energy, divided by the mass multiplied by change in temperature. Okay, this is the formula you eventually use to calculate your specific heat capacity. This is the formula you eventually, which we've labeled as equation 2, which we labeled as equation 2. This is the formula you eventually use to calculate your change in energy. Is that okay? Okay, and let's move on. Evaluating the experiment. Evaluating the experiment. Okay. When you look at the experiment, what are the things that may give you errors? Because every experiment, there's no perfect scenario. There might be one or two small, tiniest error that you may not even notice, but they exist. These errors, they exist. What are those things that may give you error? One is called the systematic error. Now, systematic error is beyond your control. Make sure that the voltmeter and the ammeter are initially set to 0 to avoid the zero error. So maybe someone used the voltmeter before and the ammeter, they didn't set it to 0, and then you just start to use it without wiping them, without like bringing them to 0 before starting to use them. So this will give you a systematic error. This will give you a systematic error. Systematic errors are faults that comes from the apparatus that you are using. The error is not from you, but it's from the fault on the apparatus or experimental method that you are using. The method you use. Either the fault is from the apparatus or the fault is from the experimental method, the method that you're using. And we say the method may be consistently affect every measurement that you take in the experiment. For example, like what we call the zero error. The zero error affects the accuracy. Maybe your measurement, instead of starting from 0, it did start from 0. Even some people, when they want to start measurement, they take their ruler, instead of starting to count from 0, like 0 to 1 is called 1, then 1 to 2 is called 2. So people just start from 1. They put the ruler, they start from 1 to 5, they call it 5. 1 to 5 is 4, if you count. Because from 1 to 2 is 1, from 2 to 3 is 2, from 3 to 4 is 3, from 4 to 5 is 4. So that's a zero error. Instead of starting from 0 to count to 5, you are starting from 1 to count to 5, and you think you have measured five things. You've not. You've only measured 4. Is that okay? So the systematic error may come from your method you are using or may come from the equipment you are using. Okay? That's one way. So in the exam, in paper 6, you say sources of error. One is systematic error. Okay? In the exam in paper 6, it's a sources of error. So one is systematic error. Error may emanate from the method you use or from the equipment themselves. That's one. Number 2, another source of error is random error. Okay, random error, not all the heat energy supply from the heater will be transferred to the block. Some will go into the environment, like we move into the surroundings. Not all that goes, not all the heat energy that you supply goes into the block. Some moves to the surroundings, some just heat up the thermometer. Some of them, instead of they heat up the thermometer itself. So these are random errors. These are errors that comes, they comes from the experiment. They are all predictable changes in an experiment, causing one measurement to differ slightly from the next one. This type of error, they affect precision. They affect the accuracy. They affect the precision. They are all predictable. They can just come. You may do it the second time. This error may not be there again, or it may be minimized. So they are called random. They just come up. They are random. They just come up. They are random errors. Okay. So we say not all the heat that you supply. For example, one example of a random error is that the heat you supply from the heater, not all of them supply to the heater. Not all of the heat is going to to heat the block. Some goes to heat the thermometer. Some is being lost to the surrounding. This means that the measurement value, of the specific heat capacity is likely to be higher than what is actually is. So one of the effects is that of error, why we have to minimize error, is that whatever the specific capacity that you've measured or you've calculated may not be the exact value. It may be slightly different from the exact value, maybe slightly higher because of some of the error that have occurred during the process of your experiment. Now, to reduce this effect, make sure that the block is fully insulated. You have to insulate the block and make sure that no heat is lost. You know, if the block is insulated, then to minimize the heat loss, you insulate the outer layer of the block. Insulate it. Don't let heat to be lost to the surrounding, because you know insulation does not allow heat to pass through. An insulator is a substance that do not allow heat to pass through them, right? So the heat, once it's supplied to it, do not easily be lost to the surrounding or be lost to the thermometer. The heat will not easily be lost to the surrounding, nor will it be easily be lost to the thermometer or be used to heat up this thermometer. So this is how to reduce the error. Insulate the block, insulate the surrounding block, except this place where you are supply the heat. And this heat is already penetrated this insulation. This heater has penetrated here to the block directly. So every other compartment, every other outlet, you have to insulate it so that no heat will be lost to the surrounding, nor the heat be lost to heat the thermometer up. So that's one way of solving this random error scenario that comes in the experiment, okay? Now, a geometer could be used to calculate the energy directly. You can use a geometer to calculate the energy directly instead of doing the energy measurement. You just bring a geometer, connect it, and whatever amount of energy that is being supplied here, a geometer will be measuring the energy that is being supplied, okay? Instead of calculating the amount from the current and the voltmeter and time taken to calculate the energy, you can use a geometer to calculate the energy to reduce error. Because all this your calculation, there may be error in the values. Another way to improve accuracy is to use a geometer. A geometer will just tell you how much energy it has supplied. So instead of measuring current, finding the average, measuring voltage, finding the average, and then multiplying by time, the difference between the final time and the initial time, instead of doing that, you say 600 minus 60, you get 540, then you use 540 to multiply the average value of current multiplied by the average value of voltage. Instead of doing that, you just use what we call the geometer. The geometer will tell you how much energy it has supplied directly, okay? How much energy it has supplied directly. So you just use that value. This will eliminate error from the voltmeter and ammeter and the stopwatch. So there are error from your stopwatch. Maybe just before you stop the time or before you start it, the reading has already begun. So there are tiny error coming from here. Tiny error coming from here. Maybe your measurement of your ammeter was not so super accurate or precise, or your measurement from your voltmeter was not so super accurate. So if you use the geometer, you reduce the error. That will be coming from the ammeter, and the voltmeter, ammeter, and stopwatch. Then again, you make sure that the temperature value is read at your eye level from the thermometer to avoid the error due to parallax. You know how to avoid error due to parallax? You come to this thermometer, okay? You make sure your eye level is here, not like you're looking from somewhere, from a distance, not like you're far away, you're looking it from this way to this way at an angle. No, you must ensure, let's show it from the board, you must ensure that if this is a thermometer, you must ensure your eye level is gauged here. Let's say this is a calibrated thermometer. Let's say this is a thermometer, okay? To avoid error due to parallax, you have to ensure that, let's say the temperature is here, let's say it's somewhere here, we want to measure here. So you must ensure that your eye level is in line of sight, There's a line of sight between your eye and the level you are measuring to avoid error due to parallax, okay? There must be line of sight. Your eye level must be in line of sight of the meniscus you are measuring, the calibration where you are measuring, line of sight. Okay, there must be a line of sight. So, there must be a line of sight.
Yeah.
There must be a line of sight. There must be a line of sight. Not that your eye is here. Not like your eye is here. Not like you come and stay here. Not like you come and stay here and you read it here. You think your accuracy. This will be wrong. But when you use a line of sight, then you avoid error due to parallax. Error due to parallax. So you avoid error due to parallax. It's very important in the exam. You must write this. How to improve your accuracy? You say avoid error due to parallax. Error due to parallax. In paper 6, how to improve your accuracy of your result. You say avoid error due to parallax. Avoid error due to parallax. Meaning, your eye level must be where you are measuring the significant location you're measuring. Your eye level must be in. You must have a line of sight. Your eye level must be on that same line in order for you to take the measurement. So if here is 50, your eye is 50, then you will measure it correctly. But if you here, you may measure here as 49. You think it's 50, but you read 49 degrees Celsius. So these are all error due to parallax. These are error due to parallax. Is that okay? Okay. So now let's talk about the safety. We told you to avoid error due to parallax. Okay. Let's talk about the safety. So the experiment can also be repeated with a beaker of water of equal mass, and then the water should heat up slower than the aluminum block. Okay. Now let's talk about the safety consideration. We say make sure never to touch the heater. Yeah. The heater is very hot, right? You ensure that you never touch the heater physically. Don't touch the heater. Don't even touch the block while it's still on. Otherwise, it will burn your skin and set something on fire. So don't touch the heater. Don't touch the heater. Don't touch the block. Okay? So you burn yourself and you might even burn the lab. Okay? That's one safety precaution you should take. Run any burns immediately or the cold running water for at least 5 minutes. If you have a burn as a result of you mistakenly touch the heater or touch the block and it burns your hand, put your hand under very cold, running cold water for 5 minutes. Put your hand under running cold water for like 5 minutes, and then the problem will be minimized. The effect will be minimized. Now, then another safety, allow time for all the equipment, including the heater, wires, and block, to cool before you packing everything after the experiment. Allow because you've just done a heat experiment. You've heated an aluminum block. So once the experiment is over, don't just start packing. You will burn yourself. So you wait for a while. Let the things cool off. Your wires, your equipment, your heater. The electric heater is still super hot. So you give time before you pack everything. It's just like when you use the electric pressing iron to iron your clothes. You don't just pack it and keep it. You hang it somewhere where out of the reach of kids, and you allow it to cool down before you eventually put it where you saw, or before you wrap it with the rope, the plug, the electrical wire. Before you wrap it and keep it, you have to let it cool down first. You don't just rush to pack it, okay? Because it's still hot, it will melt the wire. So that's exactly this is similar to what we're saying. Then another thing is that keep water away from all electrical equipment. Keep water away. All electrical equipment, they are good. Water is a good conductor of electricity. Water is a good conductor of electricity. Okay? Water is a good conductor of electricity. So keep water away from all the electrical equipment. Then another thing, wear eye protection if you use the beaker of hot water. Wear eye protection if you use the beaker of hot water. So today we'll make it short. We'll stop here. Okay, next one we will take the melting and boiling. Okay, we take this aspect. We explain the heat curve and the cooling curve. We explain the heat curve and the cooling curve. Okay, so for today we make it short. We just take 2.3, 3.3. Okay, so let's stop here because we didn't start on time. Okay, thank you very much. Thank you very, very much.